Hello and welcome to part 3 of today's IPHE presentation series, part of a series to share information from various countries on their hydrogen and fuel cell activities. The IPHE, or International Partnership for Hydrogen in the Economy, was launched in 2003 to increase global intergovernment cooperation and accelerate progress in hydrogen and fuel cell technologies. My name is Eric, and I'm the host for today's updates. Again, we're joined by 3 representatives from CSIRO who will be giving their updates. The final part 3 today is on hydrogen energy value chains in Australia. And as you may already know, the webinar is broken into 3 parts, and we encourage you to listen to them in order. So now for part 3, I welcome on David Harris, Research Director for Low Emissions Technologies, who will be going through Australia's hydrogen energy value chain. Thanks, Dave.
Thank you, Eric. As you've seen from the previous 2 presentations, CSIRO has an extensive energy program. An important part of that is renewable energy and low emissions energy technologies such as hydrogen, which is the focus of our talk today. In the low emissions technologies program, which I lead, we cover the whole value chain for many different energy technologies. So we are looking at atmospheric emissions, atmospheric chemistry. We're looking at solar and renewable technologies, and we're also considering how we bring these different technologies together. And that involves many different industries coming and working together to eventually transition to and ultimately a zero emissions energy technology system. But today we're going to focus specifically on the hydrogen energy value chains. There's a lot of activity happening in Australia, as you've seen from the 2 earlier presentations. And what we are seeing is many industries working together that hadn't otherwise worked together, different sectors of the industry beginning to work together. And on that slide there now, there's just a couple of examples of the level of activity that Australia is now seeing. There's a major project being developed in Victoria, southern part of Australia, called the Hydrogen Energy Supply Chain Project, which is led by a Japanese company, Kawasaki Heavy Industries, looking at establishing a low emissions coal-based hydrogen export industry to supply hydrogen to Japan from conversion of Australian brown coal with integrated carbon capture and storage. So a large-scale opportunity using existing resources, but with a real boost to carbon storage technologies. CSIRO is assisting those projects in the technologies, efficiencies, and, if you like, developments along those value chains. And we have established our projects right across from hydrogen production, hydrogen storage, transport, and use. We have a particular key technology associated with potential export of hydrogen around ammonia, and I'll deal with that in a moment. Our national arena, the renewable Australian Renewable Energy Agency, have also supported a wide range of what we call renewable hydrogen for export purposes. Our program is also working closely with them, looking at different technologies where we can increase the penetration of renewable energy in the hydrogen production and export chain, which of course doesn't exist yet. We have industry groups coming together, such as Hydrogen Mobility Australia, which are focused on bringing these industries together to understand and identify the markets both locally and internationally, and how the industries can pull together to actually create the appropriate market for these technologies to find their place. And as Patrick pointed out, we have a number of industry scale development and demonstration projects around Australia, including sort of research hub technology development projects, such as those that we're considering in Queensland, in Gladstone, that's indicated there. But it's really, the work we're doing is broken into 3 main areas. Patrick and Daniel have alluded to this chain. How do we improve the technologies and the commercial viability of producing hydrogen, of storing and moving hydrogen around, and of using it in end-use applications with certainly with zero emissions at point of use? So very simply, how do we make it, move it and use it around the world? Now, this value chain shown here shows it is a complex system, but it is open to many opportunities to bring in alternative sources of energy to produce hydrogen. Important to remember, hydrogen itself is not a fuel. It's not a resource which we can access. It has to be made. It's an energy carrier, and there's great prospects for using it as a carrier of renewable energy such as wind and solar, and electrolysis technologies are immediately available technology to do that. Likewise, existing technologies such as gasification of coal and biomass and other hydrocarbons is a viable existing pathway that can provide hydrogen for energy purposes on top of what it's been traditionally used for, mostly in chemical processing and manufacturing. So we have an entry here for a range of resources to feed into hydrogen production. Now, transport of hydrogen is difficult due to the relatively low energy density of the gas, and that's why we started looking at carriers such as ammonia. Now, Daniel mentioned there are many alternative hydrogen carriers, and we're certainly not ignoring any of those, but if we look at the use of ammonia, there's a significant advantage in getting these value chains activated, in that the ammonia industry is established. We have internationally now, ammonia is a heavily traded commodity, the infrastructure is in place, the shipping and transport is established, and so are the regulatory frameworks around which ammonia is traded and used. So hydrogen from renewable sources and clean sources can readily be integrated into the current ammonia production systems and into the existing ammonia transport system. So we have a pathway upon which we can grow a new industry for renewable hydrogen into energy. It's also possible to use ammonia directly in power generation applications, be it through engines, through turbines, or solid oxide fuel cells, for example. These applications haven't really been explored or exploited, but the platform, as I say, is already there, and we do have a significant amount of work now looking at how we might integrate ammonia use, which is already used heavily in the fertiliser industries, for example, into combined energy and fertiliser applications. So direct standalone power generation from ammonia stationary systems is certainly feasible. Likewise, in large-scale transport, ammonia does or could have a role in direct-fired engines for things such as trains and ships, and that's something that we're also looking at. But for today's purpose, I'd like to just highlight one aspect of that, and that's probably one of the most visible aspects of hydrogen energy, and that's vehicles for private and community use. Hydrogen fuel cell vehicles are not common, but they're certainly increasing in numbers, and Japan, Korea, and the US are seeing increasing numbers of hydrogen fuel cell vehicles. The challenge there, if we are to be exporting renewable energy from Australia to, let's say, Korea or Japan for use here in this application, is that we need to get back to very pure hydrogen. And that's a challenge on a modular and relatively small scale to do that and achieve the hydrogen qualities that are required for fuel cell vehicles. And that's where that small membrane shown on the diagram there comes into it. And CSIRO has been working for some time to develop a membrane technology that enables us to split ammonia back to hydrogen in a pure form, which is suitable for use in vehicles. Now, that's one scenario. There are other sources, as I mentioned, and I want to touch on those, of getting our renewable resources into hydrogen production opportunities. Solar thermal technologies are a really good way to do that, where we have existing processes which require heat and can be, well, if you like, the solar energy can be integrated into that through solar thermal inputs to things such as steam methane reforming, gasification processes, etc. And we do have projects on that now where we are integrating solar thermal into gas reforming reactor situations, so that we can in fact embody up to 25 to 30% of solar energy in those which were originally fossil fuel derived hydrogen products. So room for many of these technologies to come into that value chain that I pointed out earlier. Likewise, fairly established, but any hydrocarbon feedstock in principle can be converted to hydrogen. These are established technologies through gasification, syngas systems, and have been widely used for production of ammonia and liquid fuels, electricity, and of course hydrogen. But what we're able to do through the bringing together of these value chains is connect that chemical industry and its transport systems directly to vehicles, as I pointed out in the earlier slide. And that's a breakthrough that will enable rapid uptake of the technology and efficiencies of scale. CSIRO is involved in all parts of that. As I mentioned, this is just an example of some of the facilities that we have in our laboratories here in Brisbane, where we are looking at, as Daniel mentioned, electrolysis and advanced production methods for hydrogen using novel approaches, but we also have equipment and facilities relevant to existing industries, large-scale coal gasification, biomass conversion, waste conversion, etc. These sort of facilities fit very well into the development of these value chains. So an example of where those, if you like, more traditional technologies fit into the creation of this new industry, as I mentioned earlier, is the Japanese initiative in Australia, where they're looking at large-scale conversion of coal in Victoria, and ultimately looking at around 770 tonnes per day of hydrogen production. That's a major undertaking, and is a large-scale gasification project requiring integration with an extensive carbon capture and storage project. Now, that's integrated with another national activity called the Carbon Net project, where CCS Hub is being considered to bring CO2 from a range of industries for large-scale storage. So that project is an important part of both developing a hydrogen industry and also improving the economics of carbon capture and storage. In this scenario, KHI are looking to liquefy the produced hydrogen and carry that to Japan in liquid hydrogen tankers, not unlike in concept commercial LNG carriers. As you'll see on the right-hand side, the liquefaction of the hydrogen is a major, in fact the major contributor to the cost of the hydrogen, about a third of the total costs attributable to the liquefaction step itself. So there are opportunities for us to look at reducing the costs on that value chain along the ways towards the targets that Patrick pointed out in the earlier presentation. An interesting point to note is that the cost of CO2 capture and storage in this application is relatively small and therefore relatively achievable. Whereas in many previous CCS applications where power has been the primary product, the economics are certainly not as favourable. So a really important enabling project in many ways, and a real opportunity to look at hydrogen markets and export at scale. And that's where we come to some options with respect to moving renewable energy around in the form of hydrogen. Daniel mentioned some work on novel carriers. This is a diagram which sort of shows some of the options, I guess, that we have for moving hydrogen around. The three dotted lines on this graph represent ways of transporting hydrogen as hydrogen. There's a gaseous form of 200 and 700 bar, and in liquid form. And what we see there is liquid hydrogen is around about 70 kilograms of hydrogen per cubic metre, and that's what we would be shipping, and that's what would be shipped in the example that I just showed with respect to the KHI project. What we see though is with the case of ammonia, which is one of the, as I said, an established industry, a cubic metre of ammonia actually contains more hydrogen than a cubic metre of liquid hydrogen. Around about 127 kilograms per cubic metre. That gives us a much greater hydrogen density in the same volume for shipping, etc. And that's a very large economic advantage. And as I mentioned earlier, that's an established industry, so we don't need to develop the new facilities, the new liquefaction, the new transport of liquid hydrogen to get started in hydrogen transport if we go with that route. A very attractive carrier. Some of the other carriers also attractive with respect to the volumetric density of hydrogen, but many of those also have carbon associated with them, and while it's doable, it requires some additional work at the destination end to manage the net carbon emissions across the chain. So considering ammonia, the established industries based on Haber-Bosch technologies, large scale, they are high temperature, high pressure, carbon intensive processes, and that's and that's a place for us to begin. And as I showed earlier, it's possible to inject increasing amounts of renewable hydrogen into those systems. Ultimately, we'd like to directly produce renewable ammonia and potentially do it in scattered locations at sensible but relatively small modular scales. And that's why we are looking at technologies such as the example shown here of what would you call it, renewable-based direct ammonia production using, could be electrolysis and using various membrane technologies to allow us to do that at lower pressures and temperatures with lower energy inputs. And I would expect a more distributed approach to ammonia production and distribution. And now, how do we use it? As I said, it's important that we can get back to high purity hydrogen at the other end, and that's the nub of the CSIRO membrane reactor technology, where we've shown in this slide, developed a membrane that's capable of separating hydrogen from a wide range of mixed gases, if you like. In this case, we're looking at splitting ammonia to hydrogen and nitrogen and continuously removing that hydrogen through the membrane, which is 100% selective to hydrogen, and we can produce high purity hydrogen in a modular technology, which does lend itself to applications such as fuel cell electric vehicles, and opens the doorway, as I showed in the earlier slide, to using ammonia as a feedstock for vehicles in cities around the world. We have done a bit of a demonstration of this, and we've developed this technology to the scale of approximately 15 kilograms a day, which is enough to refuel 3 vehicles. And we've certainly had a successful proof of concept demonstration of that, and we're now in the process of looking for larger scale applications of that technology so that we can develop the appropriate scalability, the appropriate commercial development pathways, and also define appropriate operating conditions. You'll see, and this is a bit of an example, we did a demonstration recently where we worked with Toyota and with Hyundai, and were able to demonstrate for the first time refueling of vehicles with hydrogen derived from ammonia directly using this technology. That was a very successful demonstration and has now laid the platform for next steps, where we're looking to take that to a larger scale demonstration and integrate it with a range of hydrogen sources so that we can start to develop these technologies to the point where they will facilitate the creation of in this case, an ammonia-based hydrogen distribution industry. So the next steps we're looking at here are to produce a larger scale facility which would support something like conceptually refueling of commercial buses and cars around about 200 kilograms a day of hydrogen, and also demonstrate that other part of the value chain I pointed out of power generation directly from ammonia. So you could imagine refueling fuel cell electric vehicles and battery electric vehicles from ammonia, which could have been distributed or transported from remote areas of Australia with high solar flux to an industrial port, for example. And that's the purpose of the studies we're doing now, to bring industries together to be able to demonstrate those as we transition ultimately to higher and higher inputs of renewably sourced hydrogen, and perhaps directly renewably produced ammonia for these sort of value chains. And that's the sort of industry network that's driving a lot of this work, is bringing together a range of energy sources, more and more renewable inputs to hydrogen production, using and working with existing industries to leverage the infrastructure that we have. As Patrick pointed out in the first of these talks, the infrastructure is one of the major barriers to market activation, and the work that we're doing here is a means of leveraging existing infrastructure to get these markets started, be it for power generation, be it for hydrogen fuel cell vehicles and hybrid systems where we're bringing together power, hydrogen, renewables and clean paths to fossil fuel utilisation. So I hope that paints a bit of a picture of how the science, the technology, the markets and the industry can all come together, and how important it is to work with the industries that we have to accelerate the development of appropriate infrastructure to support many of the breakthroughs that the science and technology will make possible. Thank you.
Thank you, Dave, for that great presentation, and thank you everyone for tuning in to our three-part series on Australia and IPHE. Be sure to listen to the first two recordings in the series for more. And if you have any other questions, please visit the IPHE website at iphe.net. Thank you. Goodbye.